Welcome, brothers. Today, I'm taking you through our SOP 25 explainer. We're zeroing in on a real operational nightmare, a sudden temperature drop in the USB reactor. Now, as plant managers and wastewater operators, you already know that when that tank temperature crashes, the clock is literally ticking. We've got to set a calm but really urgent pace today to understand exactly how we can save our vital methanogen communities and get treatment efficiency back online before things go completely sideways. Okay, let's dive right into this. Here's our 6-step roadmap for today. 1. UASB tech and temperature. 2. Recognizing the temperature drop. 3. 8 root cause checks. 4. Emergency and recovery steps. 5. Long-term prevention strategies. And finally, 6. Monitoring for success. Let's kick things off with Section 1, UASB tech and temperature. This is the baseline for healthy granular sludge. So, before we can fix a broken reactor, I want to quickly reestablish exactly what makes a healthy UASB tick, right? What creates that absolute perfect environment for our granular sludge? At its core, the UASB process is this highly efficient biological engine turning high COD wastewater into biogas, mostly methane and CO2. The wastewater flows from the bottom up through that thick blanket of granular sludge, and this breakdown happens in 4 distinct stages: hydrolysis, acidogenesis, acetogenesis, and finally, methanogenesis. Now, while all the stages are important, those methanogens handling that final step, they are the absolute VIPs of our process. Honestly, they're kind of the divas of the biological world. And because they're divas, those methanogens are extremely demanding about their living conditions. They operate optimally right here at 35 degrees Celsius, give or take just 2 degrees. This exact mesophilic temperature is the absolute lifeblood of our methanogens. In fact, you can think of temperature as the single most critical environmental factor in the entire tank. It literally determines whether your plant succeeds or fails. Moving to Section 2, recognizing the temperature drop. This is what it looks like when the reactor crashes. All right, let's shift our focus to that horrible crisis moment on the floor. Things start going wrong, the temp begins to slip. I want to ask you directly, brothers, what actually happens when our tank drops below 25 degrees? Well, the answer is passive acidification. At this cold temp, our VIPs, the methanogens, they pretty much just pack up and stop working. But the acidogenesis bacteria, they keep aggressively pumping out acid. So you end up with a massive accumulation of volatile fatty acids, or VFAs. The pH plummets and your sludge just begins to float. Not good. And this brilliantly illustrates the severe consequences of that temperature drop. Over on the healthy side, a stable UASB gives you high methane production, a nice stable pH, and granular sludge that settles perfectly. But look at the failing UASB. It's trapped in passive acidification. Your VFA to alkalinity ratio spikes way over 0.5. And those precious granules end up trapping tiny CO2 bubbles. They completely lose their ability to settle, and they literally just wash right out of the tank. So, what are the immediate red flags you're going to notice? First off, your SCADA screens are going to light up with temperature alarms dipping below 25 degrees. Next, your biogas flow meter will show methane production tanking down to just 30 to 50% of normal. You're going to see really high COD in your outlet water, and you'll spot nasty patches of floating sludge right on the tank surface. Plus, when you walk the plant, you're going to get hit with this sharp, sour smell. That's the VFAs accumulating. Your pH will be dropping and your ORP will be rising. That brings us to Section 3, 8 root cause checks. This is all about diagnosing the system failure. The second you see those symptoms, it's time for a methodical, step-by-step diagnostic phase. We have to find out exactly where we're losing our heat. We start with 4 physical checks. Step 1, always verify your SCDA 4 to 20 milliamp sensors with a manual calibrated thermometer right at the inspection hole. You know sensors drift and cables oxidize, so trust but verify. Step 2, measure the inlet versus outlet wastewater temps to see if the cold is actually coming from the source. Step 3, inspect your boiler and heat exchangers. You're looking for high-pressure drops that would point to blockages. And Step 4, grab a thermal camera and scan those concrete tank walls. If you see cold patches, your PU foam insulation has either failed or it got wet, which completely destroys its insulating properties. Okay, the next 4 checks look at operations and the environment. Step 5, calculate your warm recirculation ratio from the equalization tank. Basically, is it enough to actually warm the inlet? Step 6, check your actual organic loading rate and check your sludge color. High OLRs in cold conditions are lethal, and weak sludge is going to look dark brown and break apart really easily. Step 7. Inspect your gas collection lines for blockages caused by all that floating sludge we talked about. Finally, Step 8. Check for sudden environmental shocks. Like, did a cold rainstorm flood the storm drains? Or maybe the factory is suddenly dumping cold cooling water into our system. You've got to check the surroundings. Let's move urgently to Section 4, Emergency and Recovery Steps. This is our action plan. Once we've pinpointed the cause, we need an immediate action plan to save the reactor from total failure. Listen, recovering from this can take 2 to 4 weeks if we mess it up, so I want to map out this timeline clearly so you and your management team know exactly how to pace the response. At hour 0, we hit the emergency stabilization phase. By hour 6, we transition into mechanical system recovery. And by day 3, our target is full biological stabilization. So the crucial point is right here in the first 0 to 12 hours. You must immediately cut the organic load flowing into the USVB by 50 to 70%. Just divert the rest to your equalization tank. Next, push your warm recirculation ratio up to 3 to 1 to bring that heat back up. If you have to, safely dilute the cold feed with warm water. Crucially, when you're wasting sludge, only waste the thin floating sludge on top. Never ever dump your bottom granules. And keep a close eye on that VFA and pH. Check it every 4 hours. If the pH slips below 6.8, you need to add alkalinity, like sodium bicarbonate. As we push into the 6-hour to 3-day recovery phase, it's time to fix the hardware. Stop the pumps and descale your plate heat exchangers using a 5 to 10% citric acid solution. Go ahead and repair your boilers and make sure to recalibrate the set points. Now, if your tank is losing heat through the walls, apply 50 to 100 millimeters of PU foam insulation. Seriously, proper PU foam application can single-handedly cut heat loss by 70 to 80%. Once you finally get the temperature stabilized back at 35 degrees, then, and only then, you can safely see the tank with 10 to 20% fresh methanogen sludge to help rebuild that community. All right, Section 5, Long-Term Prevention Strategies. Let's talk about winter-proofing the plant. We've saved the reactor, sure, but how do we stop this exact crisis from happening all over again next winter? Now, what's really interesting about this slide is how proactive we can actually be. Your maintenance simply has to happen in September and October, well before the first freeze. You absolutely must maintain that full PU foam or rock wool insulation, but beyond the basics, look at these bottom points. Set up automated SMS alerts that ping your phone the exact second the tank drops below 30 degrees. Ensure your stormwater and cooling drains are strictly isolated from your wastewater feed. And if you're doing future upgrades, design your equalization tanks with a covered thermal mass to act as a buffer against those sudden cold shocks. Finally, Section 6, Monitoring for Success, Tracking the Recovery. This right here is where we prove, through hard data, that our interventions actually worked. I want you using this exact post-incident log template twice a day. You're going to record the tank temperature, inlet temperature, methane flow rate, outlet COD, pH, VFA levels, sludge settling status, and of course, equipment health. Writing this down at 8 a.m. and 4 p.m. keeps the entire operational team strictly accountable to the data. No guessing, just facts. And we know the reactor is officially out of the danger zone when we hit these specific metrics. We need to see the temperatures stable at 35 degrees, plus or minus 2 for 7 straight days. Your methane flow needs to recover to over 80% of its normal capacity. COD removal efficiency must sit nicely above 70%. You should see absolutely no floating sludge, just good settling. And that VFA to alkalinity ratio, it needs to stay strictly below 0.3. I'll leave you with this powerful takeaway directly from the SOP. Temperature is the most important environmental factor. Leaving a USFB tank uninsulated in a cold region will double or triple your operating costs. So I have to ask you, brothers, is your plant truly insulated and ready for the next freeze? Or are you just sitting there waiting for an alarm to go off?